This is page 2 of the Unit 3 test, starting with problem 7. So I'm going to do my best to go through these as quickly as possible and show you my way of thinking through them. Okay, so residuals are, well, the residuals, that's just e minus y hat. So that's the, like, you could think of them as the actual minus the predicted. So this one, we've kind of worked with that a lot. So it would be C, the difference between the observed responses and the values predicted by the model. Okay, a lot of the rest of these are kind of silly. Possible models, so possible equations not explored by the researcher. So no, it's residuals are not equations. Variation in the data that is explained by the model. No, the model explains the variation in the response variable. Okay. And then data collected from individuals that is not consistent with the rest of the group. No, close. I could see how that might sound like a residual, but that's not true. It's not. Residuals are not data. They are differences. When you put a line through the data, it's the differences between the predicted and the actual. Okay, so that's one down. Okay, so which statement about influential points is true? Okay, so the first one is true. This is the main definition. Removal of an influential point changes the regression line. So you could think of it in simple terms, and we did these early on. When you have, let's say we have some data where there's really no association, and then we have another point. Well, now it looks like there's a relationship because of this influential point. As soon as you remove it, though, the line would probably be 0, no relationship at all. So that's the first one. Data points that are outliers in the horizontal direction are more likely to be influential points that are outliers in the vertical direction. So that is true, and I tried to model that in class by showing you, I told you that that was the case. But let's put enough data around here so that it's apparent that the mean for this data in the horizontal direction is right about here. Here's our range. Okay, so you may recall I put a line through the data, and then I grabbed one of these points and I pulled it up, and nothing happened to the line. The line didn't hardly move at all. Okay, it was like right there, and it didn't move at all. Okay, but when we created a point that was a significant distance in the horizontal direction, what happened was that we saw the line move and kind of get pulled down. It didn't always snap right to the point, but it got pulled down. It changed. Okay, and so we talked about points with leverage, or influential points that have leverage, so deviations in the horizontal direction can be influential points, okay, or tend to be. So influential points have large standard deviations. This doesn't even make sense. If you were thinking that they have big distance, they're different, they have big residuals, that's not really true, because you can have a point like way out here and it has leverage. It's it's a long ways away, and it does strengthen the relationship, but it has a small residual. Okay, so that's problem 8. Let's look at 9. Which is true? Random scatter in the residuals indicates a model with high predictive power. No, that's not true. Random scatter in the residuals implies that the model is appropriate. Alright? So, 2, if two variables are very strongly associated, the correlation between them is exactly 1 or -1. Well, that's not completely true either, because you can have a very strong correlation and maybe some equation fits right through it perfectly, but it's not linear, so you would not get 1 or -1 because it's not linear. It's not a linear relationship. So that's not true. The higher the correlation between two variables, the more likely the association is based in cause and effect. So no, that's not true. Just because we have a nice strong relationship with very little scatter, we could have a lurking variable that is acting on the predictor variable at the same time, acting and causing the predictor variable to go up at the same time it causes the response variable to go up. So none of these are true. They're all lies. So it would be A. Okay, 10. If this point right here was removed, if it was removed, what would happen? So we want to think of it in terms of the slope. So I'm going to work backwards, the slope and the R, the correlation. So if it wasn't there, just for a moment, we'd probably have a line, I don't know, let's see, it probably would have a line something like that. So if it wasn't, again, it wasn't there, there would be a lot of small residuals. So R would be high, okay, and this would be the slope. But it'd be the relationship would be very strong. Okay, now because of the influential point, because it's, you know, a long ways away, or a distance, a good distance from the mean in the horizontal direction, it's going to actually pull the line up. I don't know quite how much, but it's going to pull the line up. I don't think it would snap to it and touch it, because you have other points over here that are pulling the line down. Okay, so now if we removed it, then we would go back to this line. So the slope would decrease. See that? The slope would decrease. Now, when the point's there, this residual is sort of reduced maybe a little bit, but there's all these other residuals that have been made bigger. So there's more scatter with the point. So there's less scatter. At least in the scatter plot. So R would increase because the association gets stronger. Okay, so that would be D. Okay, a couple more. So 11 we already talked about. Two variables that are actually not related to each other may nonetheless have a high correlation because they both result from a lurking variable. A lurking variable acts on the predictor variable at the same time it acts on the response variable. So they both go up, but it's because of the lurking variable. Okay, last problem. They want to know if you move, see if I can draw a picture of this. I need kind of like a big graph. So this one took a little thinking, but here's a line. Okay, and so if you move, let's say you're at some point right here on the line. So if you move 1 standard deviation in x, and then instead of moving another one, you only move halfway, 0.5, what happens? How much do you go up? So, you know what? I'm going to try this again. I'm going to go, let's go out just a little bit more. So let's say 1 standard deviation is this distance. So let me approximate. So half would be about there, 0.5 sy, sx. So let's see if I can do that. So about right here would be 1. So if we go over 1 standard deviation this way, remember that the slope b1 equals r times sy over sx. So if we go over 1 standard deviation, then we would go up r, but r sy, but r is 0.6. So let me see if I can write that. 0.6 sy. Now if we went over another standard deviation, we go over about here, right? But we're not. We're only going to go halfway. So if we only go halfway, we're going to go up only half this distance. So that would be 0.3 sy. So that would be sx equals 0.5. So if we did the whole thing, if we went over this much, we would go up 0.6 sy plus 0.3 sy, so it would be 0.9 sy. So the answer would be right here, D. Okay, so I wouldn't worry too much about this one. This was just kind of a stretch problem. So, but some of these others are important. Okay, good luck.